Okay, today we're going to deal with nitrogenous compounds. Nitrogenous compounds are compounds that contain a nitrogen in its structure. We have to have a nitrogen in the structure of a compound to say that it belongs to nitrogenous compounds. Functional groups that contain a nitrogen in their structure include the cyano group, the amide group, the nitro group, the amine, and finally the diazonium salts. In case of the cyano group, we do not study it as a separate class because it can be all characters related to the cyano group can be collected from other functional groups. For example, you can prepare them through reaction of alkyl halides with a cyanide, and this is the nucleophilic substitution reactions of the alkyl halides. For their reactions, you can hydrolyze them into the carboxylic acids and you can reduce them into the amines. So generally, they are studied through other classes. The amides have been already studied through the acid derivatives. We have studied acid derivatives, and the amides were one of these acid derivatives. So today, in these lectures, we're going to be studying the nitro, whether aliphatic or aromatic, amines, whether aliphatic or aromatic, and the diazonium salts, and usually diazonium salts are aromatic. Aliphatic diazonium salts most of the time are unstable compounds and they hydrolyze easily, giving alcohols. So we only study the aromatic diazonium salts. So, as we said, we are studying the nitro group, whether aromatic nitro compounds or aliphatic nitro compounds. We're going to deal with the amines and finally the diazonium salts. So, let's start. In this video, we're going to deal only with the nitro compounds, whether aliphatic or aromatic. Next video, we're going to be discussing the amines, and in the last video, we will discuss the diazonium salts. Let's start with the nitro group as such, whether aliphatic or aromatic. The nitro group, how do we draw a nitro group? Usually you used to draw nitro groups in this form, but you never knew how exactly are these groups or these atoms attached to each other. A nitro group has a nitrogen attached to a carbon. Whether this carbon is aliphatic or aromatic, it's not a big deal, and it's doubly bonded to an oxygen and bonded to another oxygen. Okay, so if you look at the bonds between the nitrogen and both oxygens, in case of the bond between the nitrogen and this oxygen, it's a regular covalent bond. You have a sigma bond followed by a pi bond. However, this bond is not a covalent bond. This is a coordinate bond. How can you draw coordinate bonds? You can draw it in this form, in the form of an arrow between the two atoms, or you can draw it in the form of a regular bond and you add a positive charge to the atom that gave the electrons and a negative charge to the atom that gained the electrons. What is the meaning of that? It means that you had a nitrogen. The nitrogen had a lone pair of electrons on it. The oxygen had a vacant orbital, and the nitrogen donated its electrons in the vacant orbital of the oxygen. This is the meaning of a coordinate bond. We draw it in the form of an arrow showing the movement of the electrons. The electrons moved from the nitrogen to the oxygen. They were donated from the nitrogen to the oxygen, or we add a positive charge to the atom that donated the electrons and a negative charge to the atom that gained the electrons. And this is why nitro compounds, their nitrogen are electron withdrawing. Their nitrogen is electron withdrawing by induction and by resonance. Regularly, when you have a nitrogen, it's withdrawing by induction because it's highly electronegative than whatever is attached to it. However, it's donating by resonance because it has a lone pair of electrons present on the nitrogen. This is present in case of all compounds that has a nitrogen in it, except nitro compounds, because the nitrogen of the nitro compounds is carrying a positive charge. It does not have a lone pair of electrons on it to be donated in the form of plus resonance, and that's why it withdraws electrons by both induction and by resonance. We have a resonating structure inside the nitro group where the negative charge and the double bond at the oxygens, at the two oxygens, are exchangeable. We do not know which oxygen is carrying the negative charge and which oxygen is having the double bond. They keep exchanging their positions, and that's why when we draw these compounds, we say that the nitrogen is carrying the positive charge and the two oxygens are each carrying half of the negative charge and half of the double bond. We cannot specify where the double bond is, and we cannot specify where the negative charge is. It's equally distributed between both oxygens, since they are both having the same electronegativity, and thus they are both having the same ability to attract electrons. And that's why both resonating structures exist in manner. They exist exactly the same. So this is the structure of the nitro compounds, whether aliphatic or aromatic. In case of aliphatic compounds, they will be attached to an aliphatic carbon or an aliphatic chain. In case of aromatic compounds, they're going to be attached to a benzene ring. How do we nomenclate them? They are regarded as a regular substituent. So we say nitro and then alkane. You count the number of carbons in the aliphatic chain attached to the nitro group, and you name your alkane, and then you say that this alkane has a nitro group, and you specify the position of the nitro group. For example, if you have a compound like that, then this is the propane. You have you have 3 carbons, so this is propane, and on carbon number 2 you have a nitro group. This is how we nomenclate them. Simple nomenclature. Just nomenclate the alkane and then specify the position of the nitro group and name it as a regular substituent. Finally, when we deal with nitro compounds, we classify them. We have a classification as primary, secondary, and tertiary nitro compounds. How do we classify them as primary or secondary or tertiary? We have to go back first to the classification of carbons. When we say that we have a primary carbon, we mean that it is attached to 1 carbon. A secondary carbon is attached to 2 carbons. A tertiary carbon is attached to 3 carbons. So if we use this information to classify nitro compounds into primary and secondary and tertiary, you should expect that if I say primary nitro compound, then I mean that the nitro group is attached to 1 carbon. If I say secondary nitro compound, then the nitro group is attached to 2 carbons. This is impossible since the nitro group has only 1 valency. It has 1 bond attached to it. So when we deal with a functional group that is monovalent, like halogens, like the nitro group, the functional group as a whole doesn't have except 1 valency. It cannot be bonded except through 1 bond to whatever is beside it. And we start saying primary, secondary, and tertiary, we are actually dealing with the carbon that is attached to the functional group. So the carbon attached to the nitro group, in case of secondary, is carrying 2 carbons. In case of primary, the carbon attached to the nitro group is carrying 1 carbon. In case of the tertiary, the carbon attached to the nitro group is having 3 carbons attached to it. Okay, so this is the classification of nitro compounds. Primary, the carbon attached to the nitro group is attached to 1 carbon. Secondary, the carbon attached to the nitro group is bonded to 2 carbons, and tertiary, the carbon attached to the nitro group is bonded to 3 carbons. This is their classification. If we discuss something like nitromethanes, we say that nitromethanes are neither primary nor secondary nor tertiary, because the carbon directly attached to the nitro group is not attached to any carbons. It's a class by itself. Nitromethane is a class by itself. It's neither primary nor secondary nor tertiary. If we look at the organized slides, we can see that this is the structure of the nitro compounds. We have a positive on the nitrogen, negative on the oxygen, and we have a resonating structure where the negative charge forms a double bond with the nitrogen, and this double bond breaks, putting a negative charge on the oxygen. As we said, it's half negative on both oxygens and half a double bond on both oxygens. And this is the coordinate bond in its other form. As we said, we just named them as nitroalkanes and specifying the position of the nitro group, and we classify them into primary, secondary, and tertiary based on the number of carbons attached to the carbon directly bonded to the nitro group. If we need to prepare nitroalkanes, they are simply prepared from any alkyl halide, reacting it with any metal nitrite. So you add a nitro group to a metal and you react it with an alkyl halide. The nitro group replaces the halogen, giving the nitroalkane. This metal can be sodium. In this case, you're dealing with sodium nitrite. It can be silver, and in this case, you're dealing with silver nitrite. Definitely, in case of industry, we never use the silver because in case of industry, they're trying to reduce the cost of preparation of any material they are preparing. However, they only use the sodium, which is a cheap metal. Sodium nitrite. Silver nitrite, it's silver. It contains silver in its constitution, in its structure, and thus it's a very expensive material. It is only used in labs, in laboratory research labs. However, in industry, they never use silver nitrite. In industry, to prepare the nitromethane, if we look at an application on how they prepare nitromethane, in industry, they usually start with a compound that has the methane group, which is something like acetic acid, and they substitute the acid by a halogen, whether chloro or bromo. And then they add the sodium nitrite so that the nitro group would replace the halogen. So this way they have introduced the nitro group to the methane group. The only problem is that they still have a carboxylic acid group, which they lose through heating, leading to decarboxylation. Heating in presence of a base to decarboxylate the compound, resulting into the nitromethane. This is how the reaction is performed. As we said, this is how the preparation of nitro compounds is performed. You start with any alkane having a halogen on it, and then you react it with any metal, as I said, metal nitrite, whether silver or sodium nitrite, or you can use any other metal nitrite, but these are the two common metals used. You will introduce the nitro group in place of the halogen, and if your structure is what you need, then you're done. If you still have extra function groups that you do not need, like in case of the industrial preparation of the nitromethane, you will try to lose these function groups. Like, for example, in case of carboxylic acids, you will decarboxylate through heating in presence of a base. Now we have reached the reactions of the nitro group. In case of nitroalkanes, or in case of any function group, usually reactions are two types of reactions. Reactions of the functional group itself and reaction of the side chain, whether it's aliphatic or aromatic. In case of reaction of the functional group, reactions of the nitro group are only specified in the reduction reactions. Nitro groups do not perform any types of reactions except reduction reactions. There are several types of reduction, however, it's just reduction. It's the extent of reduction that we're discussing, but it's only reduction. We can reduce them through catalytic reduction, and in this case, we reach the amines. We can reduce them in acid medium where we use a metal, for example, zinc, stainless, which is tin, iron. We use whatever metal and we add acid, which is HCl, hydrochloric acid, to this metal, and again we end up with the amine. However, if we use the metal like zinc in presence of ammonium chloride and we consider this reduction in neutral medium, when we use the metal with HCl, this was reduction in acidic medium. However, if we use the ammonium chloride, if we reduce in neutral medium, we end up with the hydroxylamine. We keep one of the oxygens. In case of the other two reductions, we lost both oxygens. The reduction went to maximum extent where we lost both oxygens and we gained two hydrogens in their place. However, in case of reduction in neutral medium, we lose only one oxygen and we keep the other oxygen. These are the reactions of the aliphatic nitro compounds. In case of aromatic nitro compounds, they are exactly the same reactions. You get the catalytic reduction. You have the catalytic reduction, you have the reduction in acid medium, both giving the amines, and you have the reduction in neutral medium, giving the hydroxylamine. However, you add two more types of reduction, which are selective reduction and reduction in alkaline medium. When we discuss the aromatic nitro compounds, we're going to discuss these regular reductions in addition to two types of reductions, which are reduction in alkaline medium and selective reduction. Now, if we deal with the reactions of the side chain, we have the nitro group, as we mentioned, in this form, and it's attached to a carbon. If this carbon is carrying a hydrogen, this is an acidic hydrogen. Why is that? If we lose this hydrogen, putting a negative charge on the carbon, it will be stabilized by resonance with the nitro group. So the hydrogen on the adjacent, on the alpha carbon to the nitro group, is an acidic hydrogen that can be easily extracted by a base. Accordingly, we have the reactions of the side chain, mainly the aldol type reactions, where you can lose an alpha acidic hydrogen and then react the compound with any functional group that has a positive charge on it, like carbonyl compounds. And this is a very famous reaction, which is the Henry reaction, where you react the nitromethane with benzaldehyde, giving the condensation product. The second type of reaction that usually deals with the alpha acidic hydrogen is the Mannich reaction. We have the Mannich reactions where we have an alpha acidic hydrogen and we reacted with formaldehyde and secondary amine, resulting into substitution of the alpha hydrogen by a CH2 amine. Okay, let's discuss these two reactions. First, we will discuss the aldol. In case of the aldol, if you have an alpha acidic hydrogen, you add a base, you abstract this alpha acidic hydrogen, putting a negative charge on the carbon, which is stabilized by resonance towards the nitro group. When you add benzaldehyde to this compound, the carbonyl of the benzaldehyde is carrying a partial positive charge, so the negative charge will attack the positive charge, breaking the double bond between the carbon and the oxygen of the benzaldehyde, giving the following intermediate or transition state. and the oxygen will gain a hydrogen from the medium to produce the hydroxy compound. If your carbon attached to the nitro group doesn't have any more hydrogens, which means that it was a secondary carbon, it was a secondary nitro compound, then you should stop at this step. However, if you started with a primary nitro compound, then you have a second hydrogen on the carbon, it will produce spontaneous dehydration, resulting into the doubly bonded compound. You end up with this form of the structure if you started with nitromethane or any aromatic nitro compound. You end up with this form if you started with a secondary nitro compound. However, if you start with a tertiary nitro compound, the carbon attached to the nitro group has 3 carbons in it, which means that it has no hydrogens. We do not have a hydrogen on this carbon. Let's count the bonds at 1, 2, 3, and 4 bonds. So this is the full bonding state of the carbon. You cannot add hydrogens to this compound. So when you try to perform the aldol condensation on this compound, if you add a base, it does not have any hydrogen to be abstracted. So this, in case of tertiary nitro compounds, they cannot perform the aldol condensation with benzaldehydes. So the tertiary do not perform this reaction. The secondary will give the hydroxy form of the reaction. They will not continue to the spontaneous dehydration. The primary and the methyl both will give the double bond form. They will continue the reaction and they will give the doubly bonded compound. One nota bene that you have to take care of, which is the carbon that actually reacts with your benzaldehyde, the carbon that is directly attached to the nitro group, which means that if you have something like that, this is the nitroethane, this is the hydrogen that will be abstracted, and your product will have the double bond with the carbon directly attached to the nitro group, and whatever is attached to this group will be a substituent on this carbon. Do not react the benzaldehyde with the terminal carbon. It reacts with the carbon directly attached to the nitro group. So this is the aldol condensation. The third reaction is the Mannich. The third reaction is the Mannich reaction. Again, this is a reaction of the side chain. It deals with alpha acidic hydrogen. As we mentioned, the hydrogen on the carbon directly attached to the nitro group is an acidic hydrogen, so it can be replaced and it can be abstracted, leaving a negative charge on this carbon. In case of Mannich, you start with the formaldehyde. We have already discussed the mechanism of Mannich reaction with aldehydes and ketones, but I'm gonna just go through it quickly. You have formaldehyde, and you reacted with a secondary amine where the nitrogen of the secondary amine will attack the carbonyl since it has lone pair of electrons and the carbonyl is carrying a partial positive charge, giving the addition product like that, carrying a positive and a negative, a positive on the nitrogen which gave electrons and a negative on the oxygen that gained the electrons. The proton will leave and it will attach itself to the oxygen. This way you have a structure that looks like that. You perform this reaction in acid medium. So the acid medium will have protons that will protonate the oxygen of the hydroxy group, leaving this part of this reagent that is carrying a positive charge on the carbon and a lone pair of electrons on the nitrogen, giving a resonating structure where the positive charge is moving between the carbon and the nitrogen. This is your reagent that you actually were aiming to prepare. Once you have this reagent, it will be reacted with your compound that has the alpha acidic hydrogen, which is the nitro compound. And the nitro compound, the proton will be removed from the alpha carbon. The alpha acidic hydrogen will be removed, and the negative charge will attack the carbon, giving the electrons back to the nitrogen, resulting into a structure. This is your nitro compound, and you will add the CH2 and amine in place of the alpha acidic hydrogen. So these are the reactions of the aliphatic nitro compounds. As we mentioned, you have catalytic reduction and you have reduction in acid medium. Both end up in the amino compound. Reduction in neutral medium using zinc and ammonium chloride results in hydroxylamine. And as we mentioned, we have reactions of the side chain, and these are two types. First type is the aldol type, where you react the nitroalkanes with aldehydes like benzaldehyde, resulting in this condensation product. As we mentioned, this is only produced in case of the nitromethane and the primary nitro compounds. In case of secondary, you will have an OH on this carbon and you will not continue the condensation. And in case of tertiary nitro compounds, they do not give this reaction due to absence of the alpha acidic hydrogen. In case of Mannich, which is the second reaction of the side chain, you have an alpha acidic hydrogen attached to a carbon alpha to the nitro group. You add formaldehyde and amine, a secondary amine. You end up removing one of the alpha acidic hydrogens and adding the CH2 of the formaldehyde followed by the nitrogen of the amine. As we mentioned, you start with the formaldehyde, you attack it with the amine, giving your hydroxy compound, which is protonated in the acid medium, losing a molecule of water and leaving a positive charge on the CH2, which is stabilized by resonance. Now it's time for the nitro compound to enter the reaction, where the negative charge on its alpha carbon will attack the reagent that we have just prepared, giving the product of Mannich reaction. This way we have finished the the aliphatic nitro compounds. We will start dealing with the aromatic nitro compounds. First thing, we will deal with the nomenclature, and they are simply named as nitrobenzene. The nitro group has a very low priority. Thus, whenever there is any substituent on the ring other than the nitro group, most probably that substituent will be the parent of this compound. For example, if you have an aldehyde group, so this is benzaldehyde, and you have in the 3, at the 1, 2, 3, 4, in the 3 and in the 4 positions, you have a nitro group. So this is the 3,4-dinitrobenzaldehyde. If you have an amino group, this is an aniline, and you have in the 2 position, this is 1 and this is 2, you have in the 2 position the nitro group. So they're just regularly named as a regular substituent on benzene. Whether it's a pure or an unsubstituted benzene, it has only the nitro group on it, so it's a nitrobenzene. Or if it has other substituents, most probably the other substituents will have a higher priority than the nitro group, and thus they will just be a substituent on the substituted benzene. Now we come to the preparation of aromatic nitro compounds. We have already prepared them, and you already know how they are prepared from reactions of the benzene ring. When we discussed aromaticity, you have videos for aromaticity where we perform nitration of the benzene ring using conc nitric and conc sulfuric, and you end up introducing a nitro group to the benzene ring. If the benzene ring is unsubstituted, then the nitro group will enter whichever position because all positions are similar. However, if the benzene ring has a substituent on it, then if you nitrate if you add the nitrating agents, which are the conc nitric and the conc sulfuric, you have two options. If the Z is an electron withdrawing group, this is one option, and if the Z is an electron donating group, this is another option. In case of electron donating groups, if the Z is electron donating, then your nitro group will be introduced to the ortho and to the para positions. However, if your Z is an electron withdrawing group, your nitro group will be introduced to the meta position. Please refer to the videos of the aromaticity to remember why this takes place. Okay, however, we have a problem in case of electron donating groups, strong electron donating groups like the hydroxy and the amino groups. If you have the Z as a hydroxy group or as an amino group, we have a big problem when we perform nitration. Why is that? Because nitric acid is a strong oxidizing agent. This is the first problem, which accordingly can oxidize the amino and the hydroxy group. So this is one problem. The second problem is you have a lone pair of electrons on the oxygen and on the nitrogen that are donated to the ring, and thus resulting in huge activation of the ring. And accordingly, you will not obtain a single product as you wish, for example, the ortho or the para nitro compound. On the other, actually what you will get is the mono, you will get this product, and you will get a di substituted, and you will get a tri substituted. So you get a mixture of products. The mono substituted, the di substituted, the tri substituted, and the oxidation products, which is not a favorable case in case of organic reactions. You do not like to perform a reaction that gives a mixture of products. You prefer a reaction that gives a product and just one or two side products in a very minor amount. However, these are not minor products. These are actually, this is actually a mixture of almost equivalent amounts of products, which is not favorable. So how do we solve this problem? If you remember, whenever we had a lone pair of electrons and it was attached from both sides to double bonds, we usually said that it gives electrons to both sides by half resonance. So what we do is that we add from the other side of the oxygen and from the other side of the nitrogen a carbonyl. We say that we acylate the nitrogen or the oxygen. We acylate them. We add an acyl group, acetyl, whatever, propionic, whatever. We add just an acyl group on the other side of the oxygen and of the nitrogen, so that the lone pair of electrons of the oxygen or of the nitrogen would be distracted half the time with the benzene and half the time with the carbonyl. This way we distributed the lone pair of electrons. Instead of totally being given to the ring, they are partially given to the ring and partially given to the carbonyl, reducing the activation of these groups on the benzene ring. So this is one function of acylating. The second function is this group is a bulky group and thus producing some sort of static hindrance on the ortho position, resulting in only the para product. This is what we get, or at least a major para product with very minor amounts of the ortho products. A third function of the acyl group here is that when it produces this type of resonance with the carbonyl, it protects the oxygen and it protects the nitrogen from being oxidized. So what we do is that we acylate the oxygen, the hydroxy group, and we acylate the amino group of the substituents. So if we have a hydroxy group on the benzene, we first acylate it through any acyl halide, and then we perform the nitration which will be introduced majorly to the para position and only a minor amount to the ortho position, and then we hydrolyze the acetyl group going back to the hydroxy compound, and the same applies to the amino group. Again, you will acylate first, and then you will perform the nitration, and then you will hydrolyze the compound. Okay, so this is how we perform nitration to an unsubstituted benzene and to a substituted benzene, whether having an electron donating or an electron withdrawing on the ring. We have one problem. In case of the hydroxy and the amino compounds, as I've just mentioned, when you acylate, you end up with the para product as a major compound. However, if you need the ortho product, you will have to use a specific reagent. We call it ortho nitrating agent. As we said, if you regularly just nitrate, you will end up with the para product. If you need an ortho nitro compound, you need to use an ortho nitrating agent, which is the acetyl nitrate, where you prepare it from acetic anhydride with conc nitric acid. How does this reaction proceed? This reaction proceeds through a cyclic mechanism, where you actually first acylate. You use the acetyl nitrate to acylate the oxygen. Suppose we start with something like anisole. You have the lone pair of electrons on the oxygen, and you are using the acetyl nitrate. What happens is that you have a partial positive charge on the carbonyl, which will be attacked by the lone pair of electrons on the oxygen, and you're performing a regular acylation of the oxygen. Now the oxygen is carrying a positive charge, and it will be attached to the carbon of the carbonyl, which was carrying the methyl, and oxygen, which is now carrying a negative charge, and the ortho nitrate, and the oxygen attached to the nitro group. Now you have the nitro group directly attached, or close, it's not directly, it's very close to the ortho position of the oxygen of the anisole. This way you will have an attack from the ortho position, and now you have partial bonds. This bond is not formed yet, and this bond is not broken yet. What happens now is that, and you have a hydrogen here, which was already available on the benzene ring. What happens is that you have the bonds, it forms, and the other bonds will break. How is that? This bond breaks, forming a double bond between the oxygen and the carbon, and the bond between the oxygen and the nitro breaks, which result in that the carbon gives back the electrons to the oxygen of the anisole. So now you have the anisole. Now its oxygen has gained back its electrons. You have the hydrogen attached to the ortho position and the nitro group. Okay, and you have at the same time, you have just lost the acetic acid as an acetate part. Okay, this is what you lost, I hope. And you have the nitro group now directly attached to the ortho position. All what happens now is that the hydrogen leaves to retain your aromaticity. So now you've just introduced a nitro group to the ortho position of anisole, or to the ortho position of any benzene carrying an oxygen or a nitrogen in its structure. And you need to introduce a nitro group to the ortho position. You use the acylating agent. So this is how we prepare nitro compounds directly from benzene, by nitrating the benzene, whether the benzene is unsubstituted or the benzene is substituted. If it's unsubstituted, we just introduce the a nitro group to whichever position. If the benzene is substituted, then it depends on the substituent. If they are electron withdrawing, then the nitro group will be introduced to the meta position. If they are electron donating, the nitro group will be introduced to the ortho or para positions. As we said, the hydroxy and the amino needs to be protected before introducing the nitro group. And if we need an ortho nitro group rather than a para nitro group, we use the ortho nitrating agent. We have 3 more methods for the preparation of the nitro compounds, which we classify them as indirect methods. All what have preceded were direct methods. We just introduce a nitro group to the benzene ring. No matter how we introduce it, whether directly through nitration or orthonitration or whatever, or we acylate first. However, what we're doing is just direct methods of introduction of the nitro group to the benzene ring. However, we have indirect methods, and these are 3 methods where we actually start with an amino group and we convert the amino group into the nitro group. First, we can perform oxidation where we use trifluoroacetic acid. This is a regular oxidation where we oxidize the amino group into a nitro group in 1 step. Or we can again oxidize using what is called Carros acid, which is a sulfuric acid. It has the exact structure of sulfuric acid, but instead of having 4 oxygens, you will have 5 oxygens. This is Carros acid, where you added to again an amino compound, and it results into a nitroso, not a nitro, a nitroso. 1 oxygen, you will have a nitroso compound. When you add to this nitroso compound an oxidizing agent, which is nitric acid and sodium and hydrogen peroxide, you will end up with the nitro compound. The final indirect method that we can use to prepare these compounds is through the reaction of diazonium salts. When you start with the amine and you convert the amine into the diazonium salt through reaction with sodium nitrite and any acid, usually we use tetrafluorobaric acid, or you can use any acid. You can just add an H having a plus on it, any acid. You will end up having the diazonium salt, and this will be explained in full details in the diazonium salt class. This compound, when you reacted with sodium nitrite in presence of copper metal, it will replace the diazonium salt, introducing the nitro group in its position. So these are the methods of synthesis of nitro compounds, either directly through introducing a nitro group to the benzene ring, whether substituted or unsubstituted, or through indirect methods where you start with the amino compounds and you either oxidize them into the nitro group directly by trifluoroacetic acid, or through 2 steps by Carros acid, or you perform diazotization of the amino group, giving the diazonium salt. How this reaction proceeds is going to be given in full details in the diazonium salt class, and then you replace the diazonium group by sodium nitrite in presence of copper. As we mentioned, preparation, it's either through direct introduction of the nitro group on the benzene or on the substituted benzene, whether by electron withdrawing, it's substituted by electron withdrawing, or whether it's substituted by electron donating. And as we mentioned, the hydroxy and the amino group has a big problem, which is the multiple products that we obtain from their direct reaction with nitric acid. Accordingly, we have to protect them using acyl groups. We add an acyl group to the hydroxy or to the amino group. This acyl group serves as a protecting agent to the OH and the amino, preventing their oxidation. It decreases the activity of the benzene ring since it produces a second type of resonance in the other direction. And finally, it produces steric hindrance, preventing the production of the ortho product. It gives the para product as a major product. As we mentioned, if we need to have an ortho nitro compound, we use what is called as the orthonitrating agent, which is acetyl nitrate. It is prepared from nitric acid and acetic anhydride, resulting into a major ortho product, and it proceeds through the cyclic structure where we first acylate the oxygen and then we attack the nitro group by the ortho position, since now the nitro group is very much close to the ortho position and far away from the para position. Partial bonds are formed, and then full reaction proceeds, breaking the bond between the nitro group and the oxygen, releasing acetic acid in the form of a salt and giving the nitro group in the ortho position, and then the hydrogen leaves as a proton to retain the aromaticity of the benzene ring. As we mentioned, we can also prepare them through indirect methods, which involve oxidation of amines, either through the trifluoroperacetic acid, giving directly the nitro compound, or through Carros acid, which is a sulfuric acid having an extra oxygen, giving the nitrosobenzene, which can be oxidized using nitric acid and hydrogen peroxide into the nitrobenzene. Finally, we use the diazonium salt, where we use the aniline or the amino compound reacted with sodium nitride and an acid to give the diazonium salt, which is then reacted with sodium nitride and copper to substitute the diazonium part by a nitro group. These were the methods of preparation of the nitro compounds, of the aromatic nitro compounds. Now, if we go to the reactions of these compounds, we have, as we mentioned, two types of reactions. Reactions of the functional group, which is the nitro group, and then reactions of the side chain, which is the reactions of the benzene ring. As we mentioned, reactions of the nitro group are only reduction reactions. As we said, we have catalytic reduction, and this usually produces an amino group where we use hydrogen in presence of a catalyst, whichever catalyst you want to use. And then we have the chemical reductions, which can be in acid medium or in neutral medium or in alkaline medium. As we mentioned, in acid medium you use a metal in presence of an acid, and you end up reducing the nitro into amino group. In case of neutral, again you use zinc, however this time it's in presence of ammonium chloride, and you end up reducing the nitro group into hydroxyl amines. This is exactly like in case of aliphatic nitro compounds. In case of the alkaline reduction, it has three types of reduction depending on the strength of the reducing agent you're going to be using, and I'm going to show you how to deduce them without actually memorizing them. We have one last type of reduction, which we call selective reduction. Selective reduction is reduction of one nitro in presence of the other. If you have two nitro groups and you want to reduce only one and leave the other, you use a selective reducing agent like sodium sulfide or ammonium sulfide. And the product is that you reduce one nitro, leaving the other nitro group unreduced. These are the reduction methods that can be used for the reduction of nitro group. We have only the alkaline that we're going to discuss now. When you reduce the nitro group in alkaline medium, this is a small scheme that you can use to deduce the product according to the strength of the reducing agent. You use two nitro benzene compounds, and accordingly you will end up with two benzene having two nitrogens in between. Now, according to the strength of the reducing agent, you will change in the structure of the two nitrogens attached to each other in between the two benzene rings. If you use zinc in aqueous sodium hydroxide, this is the strongest reducing agent, and you will end up with 2 hydrogens on the 2 nitrogens. This is the maximum reduction you can reach. If you reduce the strength of the reducing agent to a certain extent, where you use zinc in alcoholic sodium hydroxide, you end up with only a double bond between the 2 nitrogens and no hydrogens on the nitrogens. However, if you further reduce the ability of this reducing agent and you only use alcoholic sodium hydroxide, which can be drawn like that, alcoholic sodium hydroxide, or we can just draw an alcohol / sodium hydroxide. This is the least reduced agent. It will have a double bond, product, and it will have a double bond between the 2 oxygens, between the 2 nitrogens, and a coordinate bond between 1 nitrogen and an oxygen. So you retain one of the oxygens. One of the oxygens will still be available as coordinately bonded to one of the nitrogens between the 2 benzene rings. How do we name these compounds? We'll start in the middle. The middle compound is having a benzene and 2 nitrogens. Nitrogens in organic chemistry are called azo or aza. So this is azobenzene, where you have 2 nitrogens in between 2 benzenes. So this is the azobenzene. In case of the top compound, you had 2 hydrogens attached to the azobenzene. So this is the hydrazobenzene. And the third product, the final one, you have an oxygen, so this is the oxazobenzene. Since you still have an oxygen, so this is an oxazobenzene. Okay, so these are the reactions of the nitro group, aromatic nitro group. As we said, they are just reduction reactions where you actually reduce the nitro group either to an amino group, or to the hydroxy amino group, or to different azobenzene compounds. Now we go to the reactions of the side chain, which is the reactions of the benzene ring. As we have already mentioned, in case of aromaticity, benzene ring can perform 2 types of reactions. The first type of reaction The first type of the reactions of benzene is the electrophilic substitution reactions. And the second type was the nucleophilic substitution reactions. And as we mentioned, the most common are the electrophilic. The nucleophilic are only discussed in case of classes introducing a positive charge to the benzene ring. And definitely the nitro group, as a strong electron withdrawing group, introduces a positive charge to the benzene ring, and thus it can perform both electrophilic substitution reactions and nucleophilic substitution reactions. It performs both types of reactions. Let's first remember what were the electrophilic substitution reactions that we know. These were the nitration, the sulfonation, the halogenation, and finally the Friedel-Crafts reactions, whether alkylation or acylation. In case of nitration and sulfonation, they can be performed in case of nitro compounds, but with some difficulty due to the deactivated ring. However, the halogenation and the Friedel-Crafts are very difficult to perform, and they are almost impossible. You cannot perform halogenation nor Friedel-Crafts reactions due to the high deactivation of the benzene ring. So we only deal with nitration and sulfonation. Let's draw the nitrobenzene and see how these reactions proceed. This is your nitro compound. You have the nitrogen carrying a positive charge. and the oxygen carrying a negative charge, and another double bond oxygen. The nitrogen will attract the electrons from the benzene. So now the nitrogen is not carrying a positive charge, and the bond between the oxygen and the nitrogen will break, putting another negative charge on the other oxygen. These double bonds I did not break. However, I broke this double bond, introducing a positive charge to the ortho position. If we stabilize by resonance, the positive charge will be moved to the para position, and further resonance, the positive charge will be moved to the other ortho position. Accordingly, the meta position did not carry a negative charge in any of these situations. The meta position is not carrying a negative charge, and accordingly, if you add an electrophile to these compounds, they will be introduced to the meta position, since it is the only position that did not carry a negative charge, and a meta position, and an electrophile is always looking for electrons. It's not looking for a positive. It's not looking for a position that is deficient in electrons. The ortho and the para positions are deficient in electrons, while the meta position is not that deficient. Accordingly, the electrophile will attack the meta position. However, if we add a nucleophile, the nucleophile is something that is looking for a positive charge. So the nucleophile will attack the ortho and the para positions. So when you react nitrobenzene with electrophiles, you end up with a meta substituent. However, if you react them with a nucleophile, you end up with ortho or para substituents. How do we perform the mechanism of these reactions? It's exactly the same in case of all the following reactions. It's one mechanism. We will not change the mechanism of this reaction. You will need to remember only one mechanism and just apply it for the rest of the derivatives. You have now the nitro with two negative charges and the positive charge inside the ring on the ortho or on the para. Once you introduce a nucleophile, the nucleophile will attack the position carrying the positive charge, whether the ortho or the para. And you still have a hydrogen at the position attacked by the nucleophile. Now the oxygen re-gives the electrons to the nitrogen, breaking the double bond between the nitrogen and the ring, liberating the liberating a hydride. This time you're losing a hydride, not a proton. You're losing a hydride to retain the aromaticity of the ring. So if you have an unsubstituted nitro compound, nitrobenzene, which has no substituents in the ortho or the para positions, you will substitute the ortho or the para hydrogen by your nucleophile releasing a hydride. However, it's more favorable if you have a halide or a nitro group in the ortho or in the para position. Why is that? If you have a compound like that, and you have a halogen, and you perform the nucleophilic substitution reaction, which proceeds exactly through the same mechanism. First, you break the bonds, perform the regular resonance, you add the positive charge, you have the chloro here, and you add the positive charge to the ortho position having the chloro group, and then you have your nucleophile which will attack this position. Now you have the chloro and the nucleophile. Again, the oxygen will give the electrons to the nitrogen to reform the bond between the inside the benzene ring, releasing the chloride. This time you're losing a chloride and introducing the nucleophile in its place. A chloride is much more stable than a hydride, so it's a better leaving group than the hydride. And the nitride is a much easier leaving group than the chloride. So in case suppose that you have a compound like that. You have here a hydrogen, you have here a chloro, and you have here a nitro group, and you introduce a nucleophile. The nucleophile will prefer to substitute the nitro group because, as we mentioned, nitrite as a leaving group is much better than chloride, much better than hydride. However, if no nitro group is present, and you have only the chloride, so it has the option of the hydrogens and the option of the chloro, it will choose to substitute the chloro because chloride is a better leaving group than the hydride. If it has no other options except for the hydride, then it will substitute the hydride. Now we have all hydrogens, so your nucleophile will substitute the hydride, whichever hydride, whether the ortho or the para hydrogen. Okay, but be careful if I draw something like that and I add a nucleophile and I ask you to perform the reaction. Do not substitute the nitro in the meta position. As we mentioned, nucleophiles only attack the ortho and the para positions. This nitro group is in the meta position, so your nucleophile will substitute the hydrogens present in the ortho and in the para positions. This way, we have finished the nitro compounds. Let's just go through the slides of the reactions of the benzene. As we mentioned, the nitro group produces a resonance, putting a positive charge at the ortho and the para positions. Accordingly, the meta position is reactive towards electrophilic substitution reactions, while the ortho and the para positions are reactive towards nucleophilic substitution reactions. We mentioned that the electrophilic substitution reactions that we know are the nitration, sulfonation, halogenation, and the Friedel-Crafts. Please go back to the aromaticity videos for these reactions. And as we mentioned, you can perform the nitration on, the nitration and the sulfonation on the nitrobenzene. However, the halogenation and the Friedel-Crafts are very difficult to be performed due to the weak electrophile used, which is the halogen and the alkyl group, and thus we cannot perform these reactions on nitrobenzene. Then we mentioned that the second type of reactions are the nucleophilic substitution reactions. As we said, you can use a nucleophile. What is a nucleophile? Anything that is having a lone pair of electrons or a negative charge in it, and you can use it to substitute a hydrogen or a halogen or a nitro group from the ortho and para positions. As we mentioned, you cannot perform nucleophilic substitution reactions on regular benzene. However, you can perform them on nitrobenzene using any nucleophile. These are just examples of nucleophiles. The following slides just include examples of nucleophiles. And the same mechanism, I just keep repeating it, once removing a hydrogen, once removing a halogen, and once removing the nitro group or the nitride group, and each time using a different nucleophile. It's exactly the same mechanism as we mentioned. You have the nitro compound. You just perform the resonance first, putting your positive charge on the ortho or para positions of the benzene, whether you have something substituted on the ortho or the para, whether the chloro or the nitro, or you don't have any substituents, it's just the hydrogen. And then you have your nucleophile that will attack the position that is carrying the positive charge, and then the resonance is reversed, releasing the hydride or the chloride or the nitride. It's exactly the same mechanism in case of all derivatives. The same mechanism where you perform the resonance, you put the positive charge on the ortho or on the para, you introduce your nucleophile, this is just a nucleophile, and then you reverse your resonance, releasing the hydride or the chloride. These are examples of different nucleophiles where you substitute the halogen with these nucleophiles. And as we mentioned, it's exactly the same mechanism. You perform the resonance, you put the positive charge at the carbon carrying the halogen, and then you reverse the resonance to release the chloride. Finally, it's the same in case of nitro group. These are different examples of nucleophiles. And this is exactly the same mechanism where you open the double bond between the nitrogen and the oxygen, breaking the pi bond in the benzene ring, putting a positive charge on the carbon carrying the nitro group on one condition, that this nitro group is in the ortho or in the para position. Again, you attack by the nucleophile, whichever nucleophile you choose, and then you reverse the resonance, releasing the nitro group. Remember that if the nitro group or the halogen is in the meta position, you cannot replace it. You only replace the hydrogens in the ortho and in the para positions. However, if the nitro group or the halogen is in the ortho or in the para position, the nucleophile will replace them, and they will be released as nitride or as chloride. This way we have finished the aliphatic and the aromatic nitro groups. Next video we will deal with the amines.